This is section 2.5. It's a theory-based one proportion z-test. So what you'll find is for every chapter, section in this book, that we always teach you how to do a simulation first, then we teach you how to do a theory-based. So traditionally, we didn't have computers. We didn't have computers to do simulations. No one wanted to do simulations by hand. And so they came up with theory-based things. We have all the proofs. We can go through and prove all of these formulas and why they work. Okay. And this is what most people use because it's more traditional. It's what you'll find in most of the research papers is these theory-based approaches. However, the simulations are really easy. Okay. And we like to teach you the simulations first. Also, the simulations are really nice because they still work for small sample sizes. Okay, so we can't always use these theory-based approaches, but when we can, we do like the theory-based approaches just because, again, they're more traditional, they're more accepted widely. Okay. First, though, before I can teach you the theory-based approach, we need to discover the central limit theorem. Very important, very, very famous. Okay, all of statistics is built on the central limit theorem. Okay, so here are some simulated distributions of possible sample proportions for various population parameters and sample sizes. So I want you to look at it and see what you notice. Okay, so first, I have pi equals 0.5 in this row. Okay, and these are different sample sizes. So at 10, notice these are all of my possible sample proportions I could get. It kind of looks like a normal curve, not really filled in yet. Not exactly like that pretty curve, but pretty close. At n equals 50, our sample size of 50, I'm getting pretty filled in. Looks very normal. At 100, I look pretty normal. At 1,000, oh, it just looks beautiful. Okay. But now let's try, what if my population proportion had been 0.2 instead of 0.5? Okay, now what do I get? So now when I look at only sample size of 10, it's actually very skewed. It has a long right tail. This is a right skew. It is not normal. Okay, but by the time I get to 50, do I look normal? I'd say I'm pretty close. I'd say I'm like almost normal. We're still not as filled in, but we're looking pretty normal. At 100, again, like almost normal. And at 1,000, yeah, I look very normal. Okay, let's try it for 0.9 though. Okay, so at 0.9 as a population proportion, now I have a long left tail, so I'm very left skew, or skew to the left. And by the time I get to a sample size of 50, I am still not normal at all. Okay. Let's see, what about 100 though? At 100, I think I'm looking probably almost normal. And by the time I get to 1,000, yeah, I look normal. Okay, I'm doing pretty good. So again, population proportion of 0.5, we started off like almost normal. We look pretty normal all the way. Okay, for lots of different sample sizes. But for a population proportion of 0.2, I started out skewed, so it takes me until I get a bigger sample to be almost normal or normal. At a population proportion of 0.9, I'm even more skewed to start with. So by the time I get to 50, I'm not normal. By the time I get to 100 though, I'm pretty close to normal. Okay, let's see. So for big sample sizes, the distribution always looks normal. For small sample sizes like n equals 10, the distribution doesn't seem very filled in. And for small sample sizes, the distribution might not be very symmetric. So now let's look at this officially with what our theory says. So the central limit theorem, again, very famous, says if the sample size n is large enough, then the null distribution of the possible sample proportions will follow a bell-shaped or normal distribution. What that tells us is that the mean of the possible sample proportions will just be pi, and we saw that before, right? Like when we looked at the mean of the null distribution, which is equal to our hypothesized proportion. And the standard deviation of all those possible sample proportions will be pi times 1 minus pi over n. Okay. So I told you we'd learn a theoretical formula. This is what it is. We can also do our simulations, and it will just tell me what the standard deviation is. Okay, but this is the theoretical one. Okay. Again, this is important because until very recently, when we got fast computers, no one wanted to have to do simulations to do significance tests. So instead of simulations, we use the theory-based approach, and we use the normal curve to find all of our p-values. So here's the central limit theorem again. It just says what we said, but I like to put it in this nice box so you can see in your notes quickly. So the null distribution of all those possible sample proportions will have shape. It will be normal if the sample size is big enough. The mean will just be equal to pi. And the SD of all the sample proportions, P, will be this pi times 1 minus pi over n. Okay. So the SD of all the possible sample proportions we had, the SD of all of that will be pi times 1 minus pi over n. So then we have this theory-based one proportion z-test. So instead of doing simulations, if our sample size is big enough, we can find the mean and standard deviation using the formulas instead of using the simulation. So then we can find our standardized statistic. Z equals, again, it's our statistic minus the mean of the null over SD the null, but we can use our theoretical formulas instead of our simulated values. Then we use the normal curve to find the probability of being farther in the tail from our z value. So like if here's your z, you just look for the area in the tail to the right or maybe to the left, depending on what you had. And that's going to be your p-value. So that looks very familiar to what we were doing, except for we didn't actually do it off of our z-value. We just did it off of like our sample count, our sample proportion. Okay, but everything else is exactly the same as what we've been doing. And the applet's really going to do all of this for us too. So it's not too hard, it's just theory. Okay. You do need to make sure your sample size is big enough. So we'll say our sample size is big enough to use the theory-based test if we have at least 10 successes and at least 10 failures in our sample. Okay. So if the sample size isn't big enough, then the possible sample proportions won't be normal, and so the p-value won't be very accurate because it's calculated using a normal curve. And we're not going to learn how we calculate that, but it doesn't need to be normal to use it. If the sample size isn't big enough to use the theory-based test, we can still use the simulations like we've been doing. Okay. The reason you have to look at least 10 successes and at least 10 failures is if you come back up here, when we had pi equals 0.2, we were skewed because it was to the right. When we had pi equals 0.9, we were skewed to the left. And so just depending on what you have, like you might have a lot of, like here at pi equals 0.2, you'd have a lot of failures and not very many successes. But at pi equals 0.9, you'd have a lot of successes, but not very many failures. So you have to check the successes and failures. Okay, so in this example, once Tic Tac claim that 74% of people tilt their head to the right when they kiss, do you think they are saying that the 74% is a statistic or a parameter? So I think when they say 74% of people, they didn't say like in our sample or anything. I think they are claiming it is all people. So that would be like a population. So that would be a parameter. So they're claiming that pi equals 0.74. So one neuroscientist, owner, was skeptical and spent time observing people at public places to see which way they leaned their head to kiss. And he actually ended up doing the same thing for like over 2 years, at least in one study. So he did look at a lot of people. But in one of his specific studies, there were 80 out of 124 pairs that turned their heads to the right. Okay. So let's go through all of our steps. So first, step 1 is state the research question. Is the Tic Tac ad correct? Do 74% of people turn their head to the right when they kiss? Or is the true percentage something different? That's what we're trying to figure out. So we're going to design a study and collect data. So we're just going to use his study. You can read the article there if you really want. He found that 80 out of 124 kissing pairs turned their head to the right. Let's see, what are the observational units? Now, in this case, it's not going to be each person that he looked at. He looked at the pairs, or you can always look at the sample size. So the sample size is 124. We can write that down, I guess, while we're talking about it. But he collected data on 124 what? He didn't collect data on 124 people. He collected data on 124 kissing pairs. So the observational units are the kissing pairs. Okay. Let's see, what is the variable and classify it? So it's just, do they turn their head to the right? And that's not numerical, that's yes or no, right? And so it's going to be categorical. And not only is it categorical, but it's even binary because it's yes or no. And so as long as it's binary, we can use proportions to deal with it. The reason we keep asking you this is we've only taught you how to do proportions, but once we teach you how to do proportions and averages on the tests, exams, once you get far enough in this class, everything will kind of be mixed up, and you have to be able to figure out, okay, should I do a proportions test on this data or an averages test on this data? Okay, so if you realize that the data is categorical and it's binary, you realize I can use proportions on this, and that's why we have you keep practicing, telling what kind of variable it is. Okay, step 3, explore the data. So like I might ask, what proportion turned their head right? Well, it said 80 out of 24. And that's the one that we're looking at. So we'll call that one p hat equals 80 out of 124. So that gives me 0.645. Okay. Let's see, what proportion turned their head left? Well, if there's 80 out of 124, I could do this a few ways. I could just subtract it from 1. So like 1 minus 0.645 gives me 0.355. Or you can think about it as, let's see, 124 minus 80 gives me 44. Like, so 44 out of 124 should give me 0.355. So there were 80 that turned their head right, 40 that turned their head left. Or sorry, 44 that turned their head left. Okay, and you can see when we're exploring the data, we always like to find some kind of visual summary, some kind of graph. So we do a bar graph. So there were 44 that turned their head left, 80 that turned their head right. Okay, let's see. Now, step 4 is draw inferences beyond the data. This is when we actually do all of our tests, all of our 3S strategy, do the hypothesis test. We often write the hypotheses back in step 2. The hypotheses can be back in step 2, or we can write them here. It just depends on when you remember to write them down. Okay. Let's see, the proportion of all people that turn their head to the right to kiss is, well, remember, what was their claim? If you go back to Tic Tac claimed it was 74% of the people. So that was their claim. So they claimed 0.74. And if I was to write that in symbols, that would be that pi equals 0.74. And the alternative, he thought that they were wrong. But did it tell me if he thought it was less than or more? So go back up, read it again. Let's see, he was skeptical. It didn't say, though, if he thought it was greater or less than. So if he didn't tell us which way he was suspicious, we have to do a two-sided test. So the alternative is the proportion of all people that turn their head to the right to kiss is, we're going to say like not or maybe different than 0.74. So my alternative hypothesis would be that pi is not equal to 0.74 because he didn't tell us which way he was suspicious in. So this would be a two-sided test. So when we pull up the applet, let's figure out what we want to put in. My probability of success, that's whatever is under your null hypothesis. So 0.74. My sample size, how many people did he look at? He looked at 124 people. Let's do at least 10,000 repetitions. And we're going to count samples as extreme as what? Let's see. We need to do greater than or equal to, what was our sample proportion? Let's do proportions. Let's see, so our sample proportion was 0.645 or less than or equal to, but I don't actually have to figure out what that number is. Actually, let's look at it. 0.74, if our center is at 0.74, then we're actually going to want to do less than or equal to 0.645 or greater than or equal to something on the other side, but I don't actually have to know what that is, okay, because the applet does it for me. So then I'm going to click the box for two-sided. So let's put all that in. So I've put everything in. Okay, I did my proportion of successes. I want it as extreme as 0.645. You'll notice that I'm going to look for everything in the tails because we didn't know if it was left or right. If I put in a less than or equal to 0.645, that gives me the tails. If I put in a greater than, well, that's going to give me the whole thing, and that doesn't really make sense. I just wanted stuff in the tails, so should be that less than or equal to. Okay, but now when I click two-sided, okay, it says 0.645 is the left side, and then it figured out for me the same distance away would be this 0.8389 going to the right. Okay, now just for a few interesting things, let's say you hadn't figured it out and you did a greater than or equal to, but then you click two-sided, it will automatically figure out, oh, you wanted the tails, and it will fix that for you. So you don't really have to figure out back on your notes, should it be less than or equal to or greater than or equal to? It will figure all of that out for you. If you just put in the 0.645 and click this two-sided, it will figure out you want the tails. And so now I can look at this and tell you that my simulated p-value is 0.0199. Okay. So that was our old approach, our simulation-based approach, but now we're going to tell you how to do the theory-based normal approximation. So first we have to check, is the validity condition met? That means we have to have at least 10 successes and 10 failures. So in this case, we had, I forgot what my numbers are, 80 people that turned their head to the right, 44 people that turned their head left. So 80 to the right, 44 to the left. So in this case, the turning to the right is a success. Doesn't mean this is better than turning to the left. It's just in statistics, we label everything as successes or failures. Okay, so 80 to the right, 44 to the left. Those are both bigger than 10. So yes, our validity conditions are met. We can use the theory-based approach. So our theory base says that for all the possible sample proportions, we should have, okay, our shape, if it's big enough, we have at least 10 successes and 10 failures, then that's a big enough sample size, and so my shape will be normal. Okay. The mean of p-hat, if you look back up at our summary box, is always just equal to pi, or our hypothesized pi, which is that 0.74. And then the standard deviation of all the different p-hats, so this doesn't mean p-hat equals this, but it means the standard deviation of all the p-hats is equal to this pi, so 0.74, times 1 minus 0.74, divided by my sample size of 124. And then you have to do the square root around all of that. So you might want to practice putting that on your calculator, 0.74 times 1 minus 0.74, divided by 124. Now, don't forget to take the square root at the very end. It gives me 0.0393. Okay. Now, my standardized statistic is you put in your statistic, which is my sample proportion of, let's see, don't forget, p-hat equals 0.645. So my statistic is 0.645 minus my hypothesized mean of 0.74. Divided by my SC of 0.0393. Don't forget to put parentheses around the top. Or put in your calculator and then hit enter. So 0.645 minus 0.74 divided by 0.0393 equals, sorry, I'm having issues here. Negative 2.42. Okay, so now let's remember, what does the Z standardized statistic tell us? It tells me that I am 2.42 standard deviations below what I'd expect if the null is true. Okay, now we already know that's more than 2 away. We're going to be suspicious. We don't think the null is plausible. We're going to have evidence for the alternative, so we have evidence that their claim of 0.74 is wrong. Okay, but let's keep going. So I can put it into my applet, so everything is the same, but now there's this option that we haven't been using. You might have noticed it says right here, normal approximation. So all I have to do is hit this normal approximation, okay, and it will draw the normal curve. It'll overlay it. You can see we look pretty close, okay, and so this value up here, the red value, is still our simulated p-value, but now this value down here is our actual theoretical p-value. Okay, it will even tell you what Z is. And an interesting thing, if you clear all this, you don't actually have to draw the samples. If you just click normal approximation, so you still count the samples, you do normal approximation, it will tell you the p-value stuff. But coming up here, notice all of my samples are gone. But what that means is this mean and SD, those are actually my theory-based mean and SD. So if you are on the test and you freeze and it tells you what should the mean be, what should the standard deviation be, just come in here, click the normal approximation. It will tell you the mean is 0.74 and the standard deviation is 0.039. Okay, which is exactly what we got. It just rounded a little bit more. Okay, and it will even tell you what the Z value is. So again, if you freeze on the test, just click the normal approximation. It will tell you the Z value. It will tell you the mean and SD. It will tell you probability. Okay, if I actually draw the samples, sometimes the mean and SD might change a little bit because if you draw the samples, they'll be based on the simulated results, not the theoretical results. But if you're doing 10,000 samples, it'll be close enough that you'll be able to get the right answer on the test. Okay, even if you've forgotten you drew your samples. So not a big deal at all. Okay, so this value up here is always the simulated p-value. Okay, a 0.0199. This is our theory-based p-value. Okay, so they're not exactly like, again, simulations are off a bit from time to time. The theory-based p-value should be the same whether you run it or I run it, because the computer's using the exact same formulas every time. Okay, it's not doing samples, it's not doing simulations, it's actually using formulas. Okay, but they're so close, okay, that no issues at all. No one's ever going to care if your p-value is 0.019 or 0.016. Okay, very close. And again, this was much easier to do without fast computers. Okay, so because we have such a large number of samples of 10,000 samples, our theoretical mean and SD match up with our summary statistics from a simulation. Okay, you can't even tell a difference. And then how close are the p-values? Well, they're pretty close. If we did the simulation millions of times, the p-values would be almost identical. Okay, in practice, we always use the theory-based approach. If possible, it's faster to do without simulations and more accepted by the scientific community. But if the sample size is too small, the theory-based approach will not be accurate. And so we have to use the simulation. And you can still use a simulation for all times, but if you're writing a research paper, you'd want to do the theory-based approach because it just sounds more official. Okay, step 5 is formulate the conclusions. So whichever way we decided to do this, okay, both of those p-values are small p-values. So we have evidence against the null, which means now we have evidence for the alternative, which is what I was hoping to show. Okay, and so then what is our actual thing that we're going to tell our boss is we would say that the long run proportion of all couples that turn their head to the right is not 0.74. Notice what's interesting here. I can't really tell him that it's less than 0.74, and I can't really tell him it's greater than 0.74 because my alternative hypothesis was just that it's different then. So I just tell him it's not 0.74. And don't forget, step 6 is look back and ahead. Okay, so these are actually quotes from his study that he did. So he looked at kissing couples in public places. Okay, he recorded which way they turned. Okay, he only looked at the first kiss because maybe after the kiss for a while they turn their head because their neck gets sore. He did have check to make sure like they actually connected lips. They weren't holding things in their hand because if you had a suitcase in one hand, you might turn. Okay, and it had to be obvious, like he had to be able to tell. He looked at subjects that ranged in age from like 13 to 70. So these are all things that would have been very useful for people to know. Okay, and as you're reading, you're like, oh, maybe he should have also checked this. That would be like a look back and ahead. And he also said, like, well, maybe my finding is linked to other forms of sightedness, for example, like favoring the right foot or ear or eye that don't become established until long after the newborn head turning preferences disappear. Okay. So these are some of the things that he put in his paper as the look back and ahead. So just to reiterate, our theory-based approach versus simulations, we should use the theory-based approach if the sample size is large enough. That means at least 10 successes and 10 failures. If the sample size is not large enough, we have to use a simulation approach. The reason why is if your sample size is too small, then our null distributions of possible sample proportions are not filled in enough, and they can be skewed, not symmetric. So in that case, the theory-based p-value will not be accurate because it's based on a normal curve. So here are some examples of simulated null distributions that would not work well for the theory-based approach because the null distributions don't look like a normal curve. So here's one where our sample size was just too small. It's not very filled in. Okay, here's another one. Our sample size is too small. It's not filled in, and it's not symmetric. So here we're almost symmetric, but not quite. Here we're definitely skewed. So like a little skewed. And this one is very skewed. And neither are filled in. When we say not filled in, it means like we only have like 10 possible choices here or like 6 possible choices here. Really, we like our normal curve to not look like individual lines, but start to look like an entire curve. Okay. And a reminder about big p-values, if you get a big p-value, that means you do not have statistical significance. We do not have evidence against the null, which means we do not have evidence for the alternative. Now, just a little caveat here, you do not say do not say we have evidence for the null. We are never looking for evidence for the null. We're always looking for evidence against the null. That's always what we're doing. And so we don't say we accept the null. We don't say we've shown that the null is this. We're saying, we didn't find evidence against it. And we will talk more about why that is as we go through this class. Okay, so one more example. Wine bottles. The natural cork in wine bottles is subject to deterioration, and then the wine can be contaminated. So it's been reported before that about 15% of bottles are contaminated. Suppose in one study they found that 3 out of 30 bottles was contaminated from the corks. Is this evidence that less than 15% of all such bottles are contaminated? Well, first of all, should we use the theory-based approach? Why or why not? So remember, we need at least 10 successes and 10 failures. So we have 3 contaminated and 27 not. So we have 27 failures, but we only have 3 successes. So no, we should not use the theory-based approach. My sample size is too small. So either we're going to be skewed or we're just not going to be filled in. Either way, our theory-based approach is not going to be accurate. Okay. My null, well, sometimes I like to do the alternative. What are they hoping to show? So they are hoping to show that, let's see, less than 15% of all bottles are contaminated. And then the null would have to be an equal sign. So it would be 15% of all bottles are contaminated. Let's put these in symbols. So my null with the 0 on it is that my pi equals 0.15. It always has to be an equals for your null. The alternative with an A is going to be that pi is less than 0.15 because I want to show that it's less than. So let's compare it to approaches where I said we can't use the theory-based approach, but I want to show you why not, what happens here. So the simulated p-value for 1,000 repetitions, if you scroll down, I put it in. So my probability of success is 0.15. My sample size is 30. I did 10,000 repetitions. I wanted to count samples with less than 3, less than or equal to 3 successes. Okay. And you can see my simulated p-value is 0.3232. It's nice. They just kept everything in the same place. That's always where our simulated p-value has been. Okay. Now my theory-based p-value though, so you just click on the normal approximation. That's how you do your theory-based. So this is my simulated. This is my theory-based. So now my p-value is 0.2216. 0.2216. Okay. So notice these p-values are quite different. Much more different than before. Either one was technically still getting to the same conclusion, but the p-values are very different. Okay, and we should use the simulation-based p-value because we already said our sample size is too small to use the theory-based. So we don't want to use this one. My sample size was too small. For conclusion though, what would we tell our boss? Well, we would say that this was a big p-value. It's bigger than 0.05. We would say we did not find evidence against the null, which means we did not find evidence for the alternative. So those are the general things for your boss. You always frame in context of the problem, and it should always be in context of the alternative hypothesis because that's what you're hoping to show. So we did not find evidence that the proportion of all bottles contaminated is less than, what do I say, 15%. So just in conclusion, again, we should not use the theory-based approach here because of validity conditions. The sample size is not met. Okay, the sample size is too small. The p-value for the theory-based approach will not be accurate, but we can still use our simulation approach and get an accurate p-value.